Right. In this section, I'm going to talk about another very interesting machine learning algorithms comes under the term instance-based representation, which means basically we will not create any model as such. So if you remember what we discussed last time, we use a data set to generate a decision tree structure. And that's what we call the model that we build from the data. But when it comes to instance-based representation, there's no model as such. Therefore, this is known as rote learning, which means you take the instance themselves as your model, right? And what happens, we use the instance themselves to make the representation. So we can say that the instance themselves will represent the knowledge. Therefore, we call instance-based learning. So that's what we are going to discuss. There are many algorithms like this. But then the problem is, how do you define what is learned? This is something like your seating arrangement in a classroom. Usually when I go to a classroom, you might see that students tend to sit together. And if you closely look at the seating arrangements, there should be some similarity among the students who sat together. So that's what exactly we are going to look at here, the similarity function. So in other words, therefore, this instance-based learning is known as lazy learning. Why we say lazy learning? Because in decision tree like algorithms, we use the data, and during the training, we build a decision tree. And during the testing, we use the tree to make predictions. But in instance-based learning, there's no model as such. I told you we use instance themselves. So which means we delay our learning process until we get some test set. So when you get a test set, then each test instance you compare with what is already in the database, the instance space, and then based on the nearest instance, you are going to make the decision. So that's what will happen in instance-based representation. So usually we talk about two main algorithms under this instance-based representation. We normally say simple nearest neighbor or one nearest neighbor, or you can say just nearest neighbor, which means that you look for the closest instance. And then more generalized version would be, we call it k nearest neighbor, which means we look for k closest nearest neighbors. I will explain those with the example. Right. So I told you like similarity is what we are going to use here. So when you get a new instance, we try to identify what neighbor instances are close to each other. So in 2D plane, this is very important. So usually we use what we call the distance function. So the distance function defines how close those instances are. So if you have like one numeric attribute, let's say you have only one attribute, then it's very simple case because you can just get the differences, right? So let's say you have one attribute and let's assume that it's a numeric one. You just take the difference. That will give you the simple distance among the two. But then again, if you have several, then usually we use Euclidean distance. Euclidean distance means we got geometrical distance. So for example, if you have x1 and x1, y1 and x2, y2, you get the difference between the x's and y's and you square them, and then you sum it up and then you get the square root. So that's what we call the Euclidean distance. So, but if you have nominal attribute, what do you mean by nominal here? Nominally in the sense like attribute like outlook, we discuss could be sunny, rainy, or overcast. If you have something like that, then how do you make the distance? So the idea is, if you have the same values, we say the distance is 0. But if you have different values, then we can say distance is 1. Right? So that's what we want to use. Okay, right. Another thing that we need to discuss. Now, since in nearest neighbor, we calculate the distances, there's a question whether we consider all the attributes. Now, let's say you assume that all the attributes are equally important. If that is the case, then you can use same weighting. But if you have different importance, then we have to use different weight vector to define what different weightages are. Right. So in mathematically, if you represent this one, so what you can do is we can simply use geometrical distance. So in this particular case, we assume that we have A1 and A2. So in this particular case, we have several attributes. Let's say we have k different attributes in this particular case, not just x1 and x2. So given a point, we have a1, a2, and we have up to ak. So you get the difference between the two attributes, square them, then you get the square root of it. So when you square, when you get the sum of squares and then you get the square root, this is called Euclidean distance. But at the same time, there's another interesting distance, which if you use just the absolute value. So you can see if you compare with the previous one, here we take the differences and then we square them. Similar to this, what happens in the down is you just take the difference and you take absolute values. This is known as city block distance. Okay. So now let's look at the distance in general. So the generalized, the distance is, we can mathematically represent like this. Given that you have two attributes AI and AJ, sorry, AI1 and AI2, you take the differences and to the power of P, and then if you take 1 out of P, which is what we call the generalized distance, we call Minkowski distance. If you assign P to 1, you will see when you put 1 here and this becomes 1, it is same as your Manhattan distance metric or city block distance metric. If you put 2 here, simply it becomes the Euclidean distance. So you can see if you provide the distance function in a generalized version like this, depend on different P values, we can different distance functions. So you can see that we can have various distance functions. Right. I hope you got some idea about how you may actually use this, right? So let me discuss with this an example, right? I want you to calculate the distances. Maybe you can take down the two distance functions first. Can you take the two distance functions? Right, these are the two distance functions. Can you take the two distance function? And when you're ready, just raise your hand so that I know you have finished taking down it. Now, here is the small exercise that we are going to do. This is what we are going to do. So what we are trying to do here is we are going to assume that we are going to work in the 2D plane. When we say 2D plane, this is the first attribute and this is the second attribute. So you can see that x1 is 1, 2, right? So that means attribute 1 is 1, 2 is 2. x2, you can see it's 3, 5. x3 you will get 2 comma 0. x4 you will get 4 comma 5. So these are the 4 attributes. Now these two are two distance matrices. In this particular case, using Manhattan distance, we calculate distance among x1 and x1. If you take the distance between the same points, you will get 0 distances. So that's what you see, 0. Next one is, what is the distance between x1 and x2? What is the distance between x1 and x2? So what you can do is, we can calculate, right? We can calculate distance between, if you say x1 and x2, x1 and x2 is, in Manhattan, we take the absolute values. So that means the difference between the two absolute values, x1 and x2, that means 1 minus 3 plus 2 minus 5. 2 minus 5. 1 minus 3 minus 2, absolute value is 2, plus 2 minus 5, that is minus 3, absolute value is 3. So you will get 5. So that means this value will be 5. Right? Try another value, x1, x3. x1, x3, distance between x1 and x3. x1 is 1. So it will be 1 minus 2. Then 2 minus 0. This is 1 plus 2, that is 3. So this is the value. So likewise, can you fill the other remaining ones and show me the answer? So let's calculate the distance among x1 and x4. So we can say D. So this is x1 comma x4. So the distance between x1 and x4, x1 and x4, 1 minus 4, 1 minus 4, plus 2 minus 5, 2 minus 5. You see that this is 3 and this is 3 again, it will be 6. So this will be 6. Similar to that, if you calculate the values, you will get like this, right? These are the values. See whether you can get these values. So what we did by creating a matrix, we know now the distance between the pairs of points, which will be useful when you want to find, nearest instances. For example, this will show you that the distance between x2 and x4 is 1, x1 and x3 is 3, right? Right. The next one. Now, this is if you use Manhattan distance, which we call, if you use the absolute values, you get the difference of these each attribute. We get the sum of absolute values. In Euclidean distance, we get the differences and you square them. You get the sum of squared values and then you get the square root. So let me see, right? So let's try to fill Euclidean now. So in case if you want to find out Euclidean distances, then you have to multiply the differences, square them, and then you get the differences. So distance between the x1 and x2 in Euclidean, so that means 1 minus 3 square. So that means 1 minus 3 square them plus 2 minus 5, 2 minus 5 square them, and then you will get the square root of this. Similar to that, if you get x1, x3, you have 1 minus 2 square, then 2 minus 0 square. You square them, you will get square root of this. Then 1 minus 4 square, two minus 5 square, you get the different square value, then you will get the square root of it. So the values you will get, right? So you will get, see whether you are getting my answer, 3.61, 2.24, then 4.24, 5.1, then 5.39. So you can see, you should have, if you have done it correctly, you should have get a Euclidean matrix like this, distance matrix. Let's say if you want to work it out as a classification problem, let's say these are like two classes. Let's say this is positive. Let me put plus here. This one also is plus. And let's say this is negative. So that means if you look at class attribute here, let me put C as a class. So what happens in the data set, you will have the class label as well. So what happens in x1, x2, x3, x4, you have class label. Actually, class label should come here, not in the distance metric here, class. So we can have the value. So we know that x1, x3 is 1. So let's say the class is positive plus x3 also positive. And this is negative. So when you have a new data point, let's say here, what happened? Let's say we have a new data point. Let's say we have new data point. So what happens now, you can calculate the distance from this point to all the other points. So the distance between here, here, right? If you take Manhattan, the distance is 1, here 2, here 4, here 5. So you see that this point is very close to this one. So the outcome of this could be taken as positive. So that's how the classification happens at the end, not in the beginning, right? That's why I told you this is a lazy learning problem. Right. Okay. So I hope you got an idea like how exactly the nearest neighbor works. We calculate the distance metric. And when it comes to parameters of nearest neighbor algorithms, you can decide which distance metric you are going to use, at the same time number of nearest neighbors as well. Right. Okay. Let's move on. Now, there are a few things we need to discuss under nearest neighbor. The first one is when you're using attributes with nearest neighbor, you have to be very careful. Because since you are getting the distances or the difference of the values using Euclidean and Manhattan, if the attributes are having various different scales, that will create a problem. Therefore, if you apply nearest neighbor algorithm, first of all, you have to normalize your data. When we say normalize, there are a few ways we can handle. And you can usually have values between 0 and 1. So common techniques, we will use it here. For example, we get a value, subtract the minimum value and divide by the max and the min. Same goes with the you subtract average value and divide by standard deviation. But at the same time, if you have a categorical value, that means if you categories, then we can take distance either 0 and 1. Further, if you have missing values, then you can say that the difference is maximum. So to discuss with this, if you look at nearest neighbor algorithms, you can often see very accurate, used for many comparative studies. But one of the problem is it's very, very slow. So for example, simple version, you have to check entire training data. So instead, people use other data structures like KD trees or bold trees for this problem. I said we assume all the attributes are equally important. If that is not the case, we should start with so we can use either attribute selection or weights. Then there could be a situation where you have a lot of noise instances that the values are not really accurate. So therefore, one way to solve this is you consider more than one nearest instances. So that's why we have algorithm called k nearest neighbor, which we use to find out what are the k closest attributes, right? And then we discuss it's very difficult. And People have used nearest neighbor from very beginning. And what they have found out is if n is goes to infinity, the ratio between k and e will also going to be less or equal 0. Right. Any questions? So we call the scikit-learn. From there, we talk about the data set. You load the data set as iris, you print iris. That's what we do. Okay. Then we separate out the data as data and then target. And we observed the first 10 rows. Then we plotted those. Then we have improved plot. Then we divide the data as training and testing. We build the decision tree. We showed the decision tree. And then we look for the predictions and we take the accuracy. So that's what we did. Right? Now, let's take nearest name. Right. Okay. So few things we won't need. We have defined X and Y, and we separate the data as training and testing. Now, when you apply nearest neighbor, I told you, standardizing your features are very, very important. Now, for that, I'm going to use pre-processing in scikit-learning. So we can say import sklearn.preprocessing import standard scaler. So what we do now, we will take the standard right. Okay, we have to say from here. Right. So the first one, what we are going to do is we say scalar. And under that, we are going to use standard scale. We use standard scalar. Then we'll say explain. We will say fit transform explain. Then we use the same to test it. Right. Now this is what we did. We separate the data into training and testing. Then we want to train the nearest neighbor model. Now, to use nearest neighbor, we have to input nearest neighbor classifier. So we can say from sklearn dot neighbors import k nearest neighbor. So we have to decide how many neighbors we want to have. Let me put number of nearest neighbors as 1 to start with. Then we fit using X-train and Y-train. We use classifier. We put the training data sets, right? So this part we did up to this point, right? This is the same as what we did it here. Then this is the training because we have selected earlier. This is what we had, right? Let me check. Same thing. So we have k nearest neighbor. We get nearest neighbor classifier. And we said number of nearest neighbor is 1. So we can say during the training, we will take classifier. Let's say CLF is you train the 2. So hopefully we have finished up to this point. Let me see whether I make any mistake. Yes, no issue. So we have fitted it. We have trained using nearest neighbor. Let's present the result. So once you present the result, we fitted and we plotted. Okay, now you can look at any errors. So I will put some classifier.predict x test. And here are the predictions. If you carefully look at, you can also identify if there are any errors. There are some errors that you can see. But for that, so we make the predictions and then we can get the accuracy score. So you can see here we are getting about 96% accuracy. Right, this is the main part that we would like to do. So we scale them. The idea is values between 0 and 1. It's easy for the reference. And then we used nearest neighbor classifier for training. One thing I would like to do is change k. So you can change the nearest neighbor here value, and then you can identify what are the best ones. What are the best ones? Right. Now, if you calculate the accuracy scores, we have seen that it's 96% accurate. But remember, this is basically by using the K value. We set the K value is to 1. So let me get this several times and let's change and we'll observe what will happen to the accuracy. So we'll take a code. So right now, the neighbors will go like this, and then we'll have accuracy scores, right? So you can see what will happen. So for example, you can have a for loop. So you can say for, let's say K in, we can have some numbers, let's say 1, let's say 3, 2, 3. Okay, so let me put range 1, 11. Let me put classify, and this is like K. And we perform this. And let's see what will happen to our accuracy values. So you can see the accuracy will vary. The accuracy will vary with various different values. So you have 96%, 90, 98, then 94. It goes on like this. So finding appropriate value for K is very important. We have to consider it in evaluating this. Right. So that's about the K nearest neighbor. Statistical model is another paradigm of machine learning, which we will use statistical modeling. So under that, we will talk about the opposite of 1R algorithm. I hope you remember the 1R algorithm. We discussed that one attribute is enough. Whereas in this one, we will consider all the attributes available. And there are two assumptions when we talk about especially naive-Bayes algorithm. We will talk about their all attributes are equally important and they are independent to each other. But we know that in practically this will not hold, but strange enough, we will get most of the time accurate classifiers. Right. Now, if you look at how naive Bayesian works, we are going to look at with the independent assumption, right? Because now this is slightly different from all the classifiers machine learning algorithm we have discussed so far. So far we have one output, either let's say play our toy problem with a data set. We discuss whether to play yes or no, but we will get only one outcome. But here we can talk about some probability estimates. What do you mean by that? Okay, instead of saying that, okay, you can play is yes, you say that, okay, 80% of the time you can play, yes. It's like in the rain, right? Nowadays we say most probably there'll be a heavy rain, right? 80% of the time. So that means there's a 20% chance that it will not rain. So this is very interesting because sometimes it's very difficult to make a clear cut what will be our outcome. Right. Then there are issues as well if you have too many redundant attributes. That means if you have identical attributes. At the same time, you can use, if your numeric attributes are not normally distributed, we have to use some kernel density estimation. Right. Now let me discuss how to calculate probability values. In this example, we will look back again our data set. Our data set of, right, the weather data set. So I hope you remember we talk about the weather data set. So maybe you can have a look at what this data set is. So maybe you can make a screenshot of this. Right. So this is the data set that we are going to consider. So here you will see and you will notice that, right, we have weather data set. We have 4 attributes: outlook, temperature, humidity, and windy. And then based on this, we are going to discuss whether to play or not. Now, what we do in naive base is, right, in naive base, we will first calculate the probability values. We'll calculate probability values. How do you calculate the probability values? You consider all the instances, right? All the instances together with the attribute values and how many times both yes and no appears. So simply we can tabulate something like this. For example, if you look at outlook, if you look at outlook is sunny, we know that there are 2 instances which classifies as yes, 3 instances which classifies as no. So likewise, you get the counts. So this can be done for overcast and rainy. Same goes with the temperature, humidity, and windy. But then again, you have to have probability values. So this is how we make the probability values for sunny, overcast, rainy. Why? When you calculate everything together, you get 9. So you said get the value and then out of 9. So 2 out of 9, 4 out of 9, 3 out of 9. So here when you add, it will be 5. So 3 out of 5, 0 out of 5, and 2 out of 5. Similar to that, if you look at the values, then you can actually calculate the fractional values. So this is the first part. Right. Let's move on. The first part, as you can see, this is just the model in naive base. That means you calculate the probability values based on your training data. So if you have different data set, you will get different counts, right? So I hope you understand. So this is the model. Now let's see, how do you find the outcome or the prediction for a new data point? So let's say we have a new day where outlook is sunny, temperature is cool, humidity is high, and windy true. Let's say we want to find out what play attribute is. We have to decide whether it's yes or whether it's no. Right, now having said that, what we do is we calculate what we call the likelihood values. So outlook is sunny, right? So when you say outlook is sunny, you go back to the table, you look at the values. If outlook is sunny, if it is yes, it is 2 out of 9. If it is no, 3 out of 5. So therefore, we will put for yes, we will get for outlook is sunny, it's 2 out of 9. For no, it's 3 out of 5. Second one is temperature cool. So you look at temperature cool, 3 out of 9 and 1 out of 5. 3 out of 9 and 1 out of 5. Then humidity is high. Humidity is high. 3 out of 9, 4 out of 5. 3 out of 9, 4 out of 5. Then windy true. 3 out of 9, 3 out of 5. 3 out of 9, 3 out of 5. Then finally the total count. Yes, we have 9 instances out of 40, 5 out of 40. And when you calculate, you get these values. But to calculate these two probability values, you have to normalize this. So when you're normalizing means when you add your probabilities, it should add up to 1. Therefore, you divide the value by the addition of the 2, which will give you like 0.205 for yes. For no, we get 0.795. So when you add this up, you will see that you will get 1. Okay. So I hope you got an idea how naive-Bayes algorithm works. So what is the model? Simply the distance calculations. Okay. Right. So having said that, we can look at, there are other issues that when we work on, right? So the first thing that I want to discuss is how do you handle when you have missing values? So sometimes calculating values or missing value will be difficult. For example, let's say Outlook is empty. We don't know. So when you want to use naive-Bayes classifier, you can just ignore this attribute and you can use the values from the other attribute. So we'll get 3 out of 9, 3 out of 9, 3 out of 9. And you multiply by the pay. So you will get this amount. Similar goes with no as well. And this is the value. When you normalize, you will get yes is 41%, no is 59%. Right. I think this is again enough. Let me show you this in the implementation. So I'm going to share this again. So here is what we have. Let me, right. Okay, so hope you can see me. Right. I will first explain how you may use a naive-Bayes, and then we can use everything together, right? So I'm going to copy paste from everything what we did. So let me start from the beginning. So what we did is simply we got the data set, right? So I'll get new code. So we load the iris data set. We separate the data. We separate the data. We split the data set. We split the data set. Then we'll get the classifier. So this is what we will get for nearest neighbor. So let me copy this. So this time we have to use multinomial. So before multinomial, let's use naive-Bayes. So we can use naive-Bayes. I'm going to use naive-Bayes here. For that, I will first use the Gaussian naive-Bayes. Then we'll say Gaussian naive-Bayes here as a classifier. And then we make the training. So once we make the training, we can calculate the predictions you will predict for test. So that's the training part. And then the accuracies. So we'll take the accuracies. Right. So let me run this. Hopefully we have done everything correctly. Yes, nothing wrong according to this. So this time it's about 98% accuracy if you use the accuracy values. So only change from the previous is we have used naive base here. All the other values will be more or less the similar. So what we have discussed is naive Bayes classifier. And in this particular problem, we discuss the implementation of naive Bayes. But what is quite popular in when it comes to natural language processing, we is called multinomial naive Bayes. It's very, why we say it's popular, particularly it's suitable because it uses discrete features. For example, in natural language processing, the matrix will be a word counts, right? Therefore, multinomial naive Bayes is quite popular. So here in multinomial naive Bayes, that particular model assumes that it follows some multinomial distribution, which is suitable for natural language processing because it uses word counts, right? So that's what we call the multinomial naive Bayes. So only change for multinomial naive Bayes is here we have Gaussian naive Bayes. Let me change this. I'm going to copy everything, right? And if you go down and if you say, if you change here to multinomial, so instead of here Gaussian naive Bayes, we will say multinomial naive Bayes. So we have to change the Gaussian to multinomial naive Bayes. And the classifier also will be then multinomial naive Bayes. And if I rerun this, right, we'll get 84 point. But remember, this is not word counts, but when it comes to word count problem, you will notice that multinomial naive Bayes is the best one. Okay, right. Okay, that's all what I have for today.